Hey everyone, and welcome to another video in our linear relationships series. So today we are going to take what we've been doing, take it just one step further, and we're going to be talking about parallel and perpendicular lines and what actually we need for two lines to be parallel or perpendicular. Now, most of this video is going to be carried out on Desmos with some activities I've prepared. But I want to start off just making some notes, just redefining parallel and perpendicular lines and allowing us to make some guesses about what we'd predict to happen and what we kind of think is going to happen with these type of lines, what they're probably going to look like, how they're going to differ or be similar. And this is just to give you hopefully a bit of an early intuition and a hint as to where we're working towards. But I kind of want you guys to have a think for yourselves as you go through this video as to how you think it's going to end up playing out. Now, let's just redefine these particular words here first. What are parallel lines? Well, parallel lines from early geometry, you may remember, these are just two lines that never meet. So these are two lines that never meet or cross. So if I were to draw an XY plane, if I were to draw two lines, any two lines, say this one, for example, and this one, these two lines look like they're kind of skewed, right? There's something about them, and we can guess that these will probably, if I were to keep drawing them out, they will probably meet at one point here. Now, the same would happen if, for example, we drew another two lines. I don't know, we went, say, this line and this line. Those are likely, if I keep drawing, those are going to meet at a point as well. Now, what do you notice I'm actually changing when I draw these different lines? For example, what am I changing, for example, with this line that I've just drawn here compared to, say, this line? What am I actually altering? Well, you can see here that I'm actually, if I were to change and rotate this line around, say I drew it again, like that, I'm changing its slope. I'm changing its gradient. And right now, if we look at this line and this line, they have two different gradients. And no matter how I draw these are two different gradients. They meet at one point. These have two different gradients. They're going to meet at one point here. And you can start to think that what is the only relationship these two can have with their gradient in order to stay parallel? Well, a gradient just means its slope. So we would want, for them to never meet, we would want these lines to have the same slope. What that's going to do, if they have the same slope, so as if the x and y change in the same way, no matter where we draw it, it's never going to meet the other line. So for example, here you can say these two have a different y-intercept. They have a different y-intercept here. Now, it doesn't really matter. What matters is that they are the same gradient. The y and the x variables in each are changing at the same rate. Now, if I get this up on Desmos to give you a better picture, I have one line here, which is y equals 2x. So this has a gradient of 2. Now, I've put another line, which once again has a gradient of 2, but I've just inserted this constant c, which will allow me to change the value of it. Now, no matter what my y-intercept becomes, whether it's negative 10 as you see here, or I put it up to, let's say, I don't know, 5.6 or 7.7 or 3.2, no matter where I go, the lines remain parallel. So if I let this just play through a little bit, you can see that, well, my intercept's changing. So it's definitely nothing to do with the intercept that makes them parallel. It is the gradient that makes them parallel. So regardless of this intercept of my blue line, what makes it parallel to the red line is the coefficient before the x, the 2, the gradient. So for lines to be parallel, let's write that down here. So for lines to be parallel, their gradients must be equal. In other words, I can show this by writing m1, the gradient of one of them, is equal to m2, the gradient of another one. So this is all we need to say that two lines are parallel. They have the same gradient. Now, let's take a look at what we mean by perpendicular lines. So I have here perpendicular lines. So these lines meet at 90-degree angles. That is the main thing we want to get when we have perpendicular lines. So if I draw another grid here, another XY plane, for something to be perpendicular, for it to meet at 90 degrees, first of all, I'll ask you guys to think about this yourselves. If I drew, for example, this one here, and this type of line that I've drawn, it has currently a positive gradient. Now, if I drew another line, this also has a positive gradient, m. So these, where they meet, they're never going to meet at 90 degrees, are they? So, as we want these lines to be crossing, we want them to crisscross in a type of way. So, all right, the positive gradient doesn't work. Let's try a negative gradient. So if I drew a gradient like this, for example, this is a negative gradient. And we can see once the gradient is in the opposite direction, so if one's positive and the other is a negative, we have more of a chance that they'll meet at a 90-degree angle. This almost looks like a bit smaller, almost looks a little less than a 90-degree angle. But that's the one key kind of takeaway that we need. So let's just make a note of that. So let's write here, perpendicular lines have gradients of opposite signs. By signs, I mean plus or minus. Now let's just explore this a little bit on Desmos, right? I have my y equals 2x, and some of you intuitively may think, okay, well, my other gradient has to be negative, so why don't I just try negative 2x and see what happens? Now, if I draw that one in, you can see they crisscross in a way we'd like, but you can see the angle they make with one another doesn't really look too much like what we want. So we're going to keep this negative, but what if we try making the 2 a smaller number? Because that's going to make the slope a little bit more gentle. So instead of the 2 here, let's try, say, 1. Okay, whoops. Oh no. Y equals negative x. All right, this looks a little better. It's kind of meeting at closer to a 90-degree angle, and it's still not quite there though. You can see, looking at this section here, they make an angle that's a bit smaller than 90 degrees. So we want an even smaller gradient. Now, why don't we just play around with, let's try, because it's got to be something smaller than 1. So what does that mean? Well, it means we're starting to look now into the fractions, these portions of 1, these not whole numbers. So we want it a bit smaller. So let's try, I don't know, let's try negative, let's try negative a half. Okay, this now looks a lot more promising. So this angle here now looks like it makes a 90-degree angle. But how does that work, right? Let's just make a little note here. So these worked, for example, when I had a gradient here of 2. And my gradient here was negative 0.5 or negative a half. Now, let's see if we can pick up some similarities here. Well, similarities or differences. Well, one thing is that the signs changed. Here, this number's negative, while we had a positive 2 here. And notice we had a 2 up here, and now we have a fraction with a 2, 1 over this same number on the denominator. Now, it might just be a coincidence. Let's try this with another value. Sorry, I just realized this signs wasn't written very nicely. Let's do that down here real quick. Of opposite signs. Okay, let's try, for example, if we made this one 3x. Okay, now I can see that let's do a nicer number. Let's do 4x. So I've made my first graph, my red graph, a lot steeper now. And we can see now my negative a half doesn't really cut it anymore. I need to make the gradient, I need to make the slope even more gentle. I want to compensate as this red line gets steeper, my other line has to get gentler. It has to balance this thing out. So, okay, we'll try 0.5. What if we did, for example, I don't know, 0.3? Okay, it's looking a bit better, but you can see there's still a little bit of a, if you kind of angle your head tilted over, you can see this still isn't quite 90 degrees. So what if I try 0.25? Okay, now we're talking. If you look at this here, if you tilt your head across, you'll see that my black line is perfectly perpendicular to my red one. They make a 90-degree angle beautifully. So as my gradient of my first one got bigger, the gradient of my other one had to get, as my first one, got steeper, my other one had to get gentler. So I had to make it a little bit smaller in the negative direction. So let's look at the other example we wrote here. So the example we had where one gradient was 4 and the gradient of the other one that was perpendicular was negative a quarter or negative 0.25. And once again, we see this pattern happening. We see, okay, a 4 here, and the sign was flipped again. It was changed, so we had to get a negative sign. And once again, we got the 4 on the denominator here. Now, these numbers have a very special relationship with one another. Now, my negative half and 2, these are what we call negative reciprocals of one another. So it's a negative reciprocal because we put a negative in front. This one's positive 2. This one's negative a half. And a reciprocal is this idea of when you flip a number or a fraction. So for example, 2 over 1 its reciprocal is going to be 1 over 2. Because 2 I can write as just 2 divided by 1. Any whole number I can just write as a fraction divided by 1. Now, this thing here is the reciprocal. That's what we call it when we flip this. Now, negative a half and 2, these are negative reciprocals. And the same goes for negative a quarter and positive 4. These are also negative reciprocals. So, and these always end up being perpendicular lines to one another. So we can think of a line perpendicular to another when their gradients, that's an important thing to note here, we're only talking about their gradients, when their gradients are negative reciprocals of one another. So let's just write that down here. So two lines are perpendicular when their gradients are negative reciprocals of one another. Now, what's a way we can just write this so you can take it home with you and say, okay, cool, this is the actual maths for how I'd find this. Before, we wrote that for these parallel lines that their gradients were equal. So to show that these are negative reciprocals in maths terms, to give you a formula to take home, the gradient of one is the negative reciprocal of the other. So that means that one gradient, if I'm given one gradient and I want to find a perpendicular gradient to that, the gradient of a line perpendicular to that, I'm going to flip this, make it a fraction, 1 over another thing, and I'm going to stick a negative sign in front of it. Another way to think about these, which some of you may prefer, is that if I multiply the two gradients together, I get negative 1. So for example here, negative a half times 2, so 2 lots of negative a half, that gives me negative 1. Same here, 4 lots of negative a quarter give me minus 1. So if I find 1, I can set up this equation here on the right and then end up solving for my unknown gradient. So that is how we can investigate parallel and perpendicular lines. So if you want just to practice, because perpendicular lines get a lot of people. Parallel is a bit easier because they're just equal. They're always going to be equal. So if we, for example, had that the gradient of one line is 2 on 3, the gradient of a perpendicular line, that is going to be equal to a negative in front and then flipping the two fractions. So finding the reciprocal, the fraction flipped over. That gives me negative 3 over 2. If I tried another example, if my gradient of one of them was, for example, negative 7, the perpendicular line to that has a gradient, sorry, I should have written this, m2, perpendicular line, gradient m2, equals, we flip a negative in front, so we have a negative 7, that gives us a positive, and 7, I can write as 7 over 1, if we flip that, I get positive 1 over 7. So Parallel and perpendicular lines depend completely on the gradient of the two lines and nothing else. These are relationships with the gradients. Now, parallel lines have equal gradients, perpendicular lines have gradients that are negative reciprocals of one another. And I've shown this here in my notes. That is a way we can write these out, which may be easier for you to work with. But thank you so much for watching, guys, and I'll catch you in the next video.